Newton's second law in terms of momentum. So we're gonna define a linear momentum P, which is product of mass and velocity, or mass times velocity, and the unit is unit of mass is kilogram and the unit of velocity is meter per second. So the unit of linear momentum is kilogram meter per second. We have one example. What is a linear momentum of a 4-gram NATO SS-109 bullet traveling at 950 meter per second? First of all, we need to convert grams to kilogram. That is, jump 3 decimal place left. Then linear momentum is mass times velocity. That gives us 3.8 kilogram meter per second. So F net force equal to mass times acceleration, and acceleration is a rate of change of velocity, or change in velocity or change in time. And we rearranged mass times change in velocity, that is change in momentum. This last is just Newton's second law in terms of change in momentum rather than mass and acceleration. In fact, this is the proper definition of Newton's second law. So the net force equals to rate of change of momentum. Example, a 6 kilogram object increased its speed from 5 meter per second to 25 meter per second in 30 seconds. What is net force acting on it? So we just defined Newton's second law, which is net force equal to rate of change of momentum. Change in momentum equals to change in mass times velocity. As a mass is constant, then we can take it out. So mass times change in velocity, and a change in velocity is normally final velocity minus the initial velocity. So the net force equals to rate of change of momentum equals to mass times change in velocity, which is final velocity minus initial velocity, divided by time taken. The mass is 6 kilogram and final velocity is 25. Initial velocity is 5, so 25 minus 5 divided by time taken is 30 seconds. That gives us 4 Newton. So net force acting on it is 4 Newton. This is a linear momentum formula, and we have a kinetic energy formula. So shows that kinetic energy can be calculated directly from the momentum using the following. We have a new equation. Kinetic energy equals to momentum squared over 2 times the mass. So we can actually derive the last kinetic energy expression from mass times velocity. We may obtain velocity equals to momentum divided by mass. Then we have kinetic energy formula, 1/2 mass times velocity squared. So we substitute velocity equals to momentum per mass into that expression, which is going to be 1/2 m p over m, whole thing is squared. Then we get 1/2 mass times p squared over m squared. So 1 over the m cancel out. That gives us p squared over 2m, and we proved kinetic energy expression. Practice. What is the kinetic energy of a 4-gram NATO SS-109 bullet traveling at 950 meter per second and having a momentum of 3.8 kilogram meter per second? Let's use the new formula we just derived. EK, kinetic energy equals to momentum squared over 2m. Momentum is 3.8, so 3.8 squared divided by 2 times mass is 0.004 kilogram. That gives us 1800 joule. Collisions. A collision is an event in which a relatively strong force acts on 2 or more bodies for a relatively short time. The Meteor crater in the state of Arizona was the first crater to be identified as an impact crater. Between 20,000 to 50,000 years ago, a small asteroid about 80 feet in diameter impacted the Earth and formed a crater. Beautiful. Cosmic collision between two galaxies, UGC 06471 and UGC 06472. Although this type of collision is long-lived by our standards, it is short-lived as measured in the lifetime of galaxy. So this is two galaxies colliding. Consider two colliding pool balls. Let's take a look at. Before phase. This is during the phase. And we have after phase. If we take a close-up look at the collision between two bodies, we can plot the force acting on each mass during the collision versus the time. Before collision and closed system, and this is during collision. Take a look at the magnitude of the force. Newton's third law applied, action and reaction. When they are closer, the force increase. And this is during phase. And after collision, we have this. Before collision, the net force between these two is 0. During the collision, the net force increase to maximum value and then to minimum value and then becomes 0 after collision. So we can see a perfect symmetry of the action and reaction force pairs. Impulse and force time graphs. Although force varies with time, we can simplify it by averaging it out as follows. So you have force time graph. Imagine an ant farm, 2 sheets of glass with sand in between, filled with the sand in a shape of above force curve. We now let the sand level itself out by tapping or shaking the ant farm. The area of the rectangle is the same as the area under the original force versus time graph. The average force F is the height of this rectangle. We can see from the graph. We defined a new quantity called impulse J as the average force times the time. This amounts to the area under the force versus time graph. If a force versus time graph is given, area under is equals to impulse, and impulse equals to force times time, and which also equals to area under the force versus time graph. Since F equals to rate of change of momentum, we have seen this before, we see that force times time equals to change in momentum. So impulse is force times time, also a change in momentum. And so we can interpret the impulse as a change in momentum of the object during the collision. So we have our expression. Impulse equals to force times time, which is equals to change in momentum. And if it's a force versus time graph is given, the area under the graph is impulse. It's well to point out here that during the collision, there are two objects interacting with one another. Right, so we have seen this. Because of Newton's third law, the forces are equal but opposite, so that F equals to minus F. Thus, for one object, the area is positive, while for the other object, the area is negative. That means the rate of change of momentum of the one object is equal and opposite direction to the rate of change of momentum of the another object while they are colliding. 0.14 kilogram or 140 gram baseball comes in at 40 meter per second, strikes and goes back out at 50 meter per second. If the collision lasts 1.20 millisecond, a typical value, find the impulse imparted to the ball from the bat during the collision. Since velocity is a vector quantity, then the momentum is mass times velocity. Therefore, momentum is a vector quantity with direction. Let us choose to the right as positive. Initially, the baseball is traveling to the left, so velocity should be negative. That's before. After collision, the baseball is traveling to the right, which means the velocity should be positive, as we choose to the right as positive reference. So, initial velocity, the baseball is traveling to the left, so initial velocity is minus 40 meter per second. And initial momentum of the baseball is mass times velocity, and the mass is 0.14 kilogram times minus 40. That gives us minus 5.6 kilogram meter per second. After collision, the baseball is traveling to the right, so final velocity is plus 50 meter per second, and the final momentum equals to mass times velocity. Mass is 0.14 times the velocity is 50. That gives us positive 7 kilogram meter per second. So the question asking the impulse, and impulse is change in momentum. So impulse equals to change in momentum, and the change in momentum is final momentum minus initial momentum. Final momentum is 7 minus initial momentum is minus 5.6. So minus minus becomes plus, and we get 12.6 Newton second. A 0.14 kilogram baseball comes in at 40 meter per second, strikes a bat, and goes back out at 50 meter per second. If the collision lasts 1.20 millisecond, a typical value, find average force exerted on the ball during the collision. Net force equals to rate of change of momentum. Force equals to impulse over time taken. Impulse is change in momentum. Well, we learned this before. Net force equals to rate of change of momentum. Change in momentum in previous slide is 12.6, and the time taken is 1.2 millisecond. Millisecond, which converted to second, which is times 10 to minus 3. That gives us 10,500 Newton. A bat striking a ball imparts a force to it as shown in the graph. Find impulse. Impulse is area under the force versus time graph. We may use trapezium formula. Here, let us use a more simpler version. We break down the graph into simpler area of rectangles and triangles. Area 1, which is triangle, and the triangle is 1/2 base times height. Base is 3, height is 9. That gives us 13.5 Newton second. Then we move on to rectangle. 4 times 9, which is 36 Newton second. And lastly, we have a similar triangle. So 1/2 times the base is 3 and the height is 9, which is 13.5 Newton second. And the total area equals to A1 plus A2 plus A3. That gives us 63 Newton second. And let's take a look at how does a jet engine produce thrust. A jet engine sucks in air at about the speed that the plane is flying through the air, heats up, and expel it as a greater velocity. The jet engines take the air at about the speed that the plane is flying through the air, heats it up. So when heated up, the velocity of course increase, right? And explained as a greater velocity. The momentum of the air change since its velocity does, and hence an impulse has been imparted to it by the engine. As we know, impulse is change in momentum. So we have a change in velocity, and mass times change in velocity, we have change in momentum. Momentum of the air change since its velocity does, and hence an impulse has been imparted to it by the engine. And based on Newton's third law, the engine feels an equal and opposite impulse. Therefore, the engine creates a thrust. So example shows that F equals to delta M over delta T times V. We know Newton's second law, the net force equals to a rate of change of momentum. Momentum is the mass times velocity. If the velocity is constant and if we have a changing mass, then we have the following expression. So velocity is constant. Now we have a rate of change of mass. The equation F equals to rate of change of mass times a constant velocity is known as a rocket engine equation, because it shows us how to calculate the thrust of a rocket engine. A rocket engine consumes fuel and oxidizer at a rate of 275 kilogram per second. That is a rate of change of mass, and used a chemical reaction that gives the product gas particles an average speed of 1,250 meter per second. That's a constant velocity. Find the thrust produced by this engine. The unit of delta M over delta T are kilogram per second, so that clearly delta M over delta T is 275, and it has a constant velocity of 1,250. So we use a rocket engine equation, that is rate of change of mass times velocity. So 275 times 1,250, that gives us 344 kilonewton. Conservation of linear momentum. This is very important. Newton's second law is net force is proportional or equal to rate of change of momentum. If the net force acting on an object is 0, we have this, and that gives us change in momentum equals to 0. In words, if the net force is 0, then the momentum does not change. P is constant. So we have conservation of linear momentum. If the net external force is equals to 0, then the momentum is constant. Example of conservation of linear momentum. A 2,500 kilogram gondola car traveling at 3 meters per second has 1,500 kilogram of sand dropped into it as it travels by. Find the initial momentum of the system. The system consists of sand and car. They are closed system. Let's take a look at the initial momentum of the gondola car. Initial momentum of the gondola car equals to mass of the gondola car times the initial velocity. Mass of the gondola car is 2,500 and initial velocity is 3. So that's give us 7,500 kilogram meter per second. Now let's take a look at the initial momentum of the sand. That is mass of the sand times initial velocity of the sand. Initially, the sand is stationary. Initial momentum of the sand is 0 kilogram meter per second. So the initial momentum of the system equals to initial momentum of the car plus the initial momentum of the sand. The initial momentum of the sand is 0 plus the initial momentum of the car, 7,500. That gives us 7,500 kilogram meter per second. Find the final speed of the system. There's no external force acting on the system or the car, and sand is a closed system, so initial and final momentum are equal. We found the initial momentum, which is equals to 7,500 kilogram meter per second, which is equals to final momentum based on the conservation of linear momentum. And the final momentum equals to, as we know, the sand drop onto gondola car. So the total mass is going to be the mass of the gondola car plus the mass of the sand, and they travel with the same velocity. So final momentum is equals to mass of the sand, which is drop into the car plus the mass of the car, and they travel with the same velocity. So mass of the sand is 1500 and the mass of the gondola car is 2500. Add them times final velocity. That gives us 4000 times the final velocity. And we need to equate initial momentum equals to final momentum. Initial momentum equals to 7500 and the final momentum equals to 4000 times the final velocity. And the final velocity gives us 1.9 meter per second. So what is the average force on the car? Normally you can find average force using Newton's second law, which is the net force equals to rate of change of momentum. Rate of change of momentum, final momentum minus initial momentum divided by time taken. Take out the mass, which equals to mass times final velocity minus initial velocity divided by time taken. Here we are looking at the average for force on the car, so that has to be the change in momentum of the car. That gives us minus 611 Newton.